My dear students, welcome in math lecture. Myself, Mitesh Bhatasna. Now in this lecture, we see R equivalence class and portion of A by R. So to understand our new topic, R equivalence class, we start our topic with the example. So to understand the definition of R equivalence class, we first see example to better understand the topic of the R equivalence class. So now consider set A equal to 1, 2, 3, and we take relation R on set A as like 1, 1, 1, 2, 2, 1, 2, 2, and 3, 3. So now observe, our relation R is first of all reflective because R contains the pair 1, 1, 2, 2, and 3, 3. So R is reflective relation. Now also R is a symmetric relation because R contains the pair 1, 2, then R also contains the pair 2, 1. So our relation R is symmetric relation. Now also observe, our relation R is transitive. For AB, BC, then AC is the 1, 2, and R contains the pair AC 1, 2. 1, 2, AB, BC, then R contains the 1, 1. Also satisfy our condition. Now 2, 1, AB, BC, then our AC is the 2, 1. R contains the pair 2, 1. Or we take AB and BC this one, then AC is 2, 2. And R also contains the pair 2, 2. And now observe here 2, 2, AB, BC. Then R contains the pair 2, 1. So R also contains the pair 2, 1. And last 3, 3 is single pair, just AB. So not need to check condition for 3, 3. So finally our relation R is reflective, symmetric, and transitive. So the definition of equivalence relation for relation R is equivalence relation. Now we define one set as a structure of set as we take y where 1 related to y. So here we define one set. Set contains the element y, but those elements come in this set who satisfy this condition means y is related with the 1, then y belongs in this set. So which element related with 1? So here observe 1 related with 1 itself. So first member of this set is the 1. Now observe 1 related to 2. So our second y is the 2. So also set contains the element 2. Now here just we have two pairs 1, 1 and 1, 2 related with the 1. 1 related to 1 and 1 related to 2. So our set just contains the two pair 1 and 2. Now here we define another set as y is 2 related to 1. So which elements come in this set? In this set contains those elements who related with the 2. So now observe which element in R related with the 2. So here first element 1, 2 related to 1. That means 2 related to y. So y is the 1. Now 2 related to 2. So also 2 related to 2. So again this set contains two elements 1 and 2. Now we define another set as y where 3 related to 1. So here which element come in this set? In this set contain those elements who related with the 3. So observe in which element related with the 3. So just only one element 3 itself related with itself. 3 related to 3. So just contain the one element 3. So now here we define three sets. first, second, and third. So this will be equivalence class generated by element 1. This is denoted as notation close bracket into 1 in suffix r. So this will be equivalence class, read as the equivalence class generated by 1. So in this set contain those elements who related with the 1. So now observe which element related with the 1? 1 and 2. So our equivalence class of 1 contained here 1, 2. Now see second one is generated by the 2, means this second our set contains those elements who related with the 2. So this is the equivalence class generated by element 2. So this set contains those elements who related with the 2. So observe which element related with the 2. So 1 and 2 related with the element 2. So this is the equivalence class generated by 2. Now last one is the generated by element 3. R denote our relation, and this notation read as the equivalence class generated by element 3. So this set contains those elements who related with the 3. So here just one page 3, and just 3 related with the element 3. So R just contained here 3, just only one element 3. So this was the equivalence class. So in general we write the definition of equivalence class as with the relation R defined as the what, where x related to y. So this is the in general definition of equivalence class. Now for any x is the member of set A. Now here our 1, 2, 3 is the member of set A. Similarly here x belongs to A, equivalence class of, so here we write the equivalence class of 1, we can write equivalence class of 2, and we can write as equivalence class of 3. So here maximum equivalence class of set A is 3, 1, 2 and 3. So similarly we find equivalence class of in generally for x belongs to A, equivalence class x with the whatever relation defined is equal to y, where x related to y. So equivalence class is nothing but the one kind of set. Equivalence class contains those elements who related with the element s. So equivalence class contains those elements who related with the s. So this was the equivalence class. Now here we take another example. We consider set A is equal to Z, and we define as relation R as xy, x minus y is the real number. So here relation is xy, where x minus y is the even number. So we already know Z contains the element infinitely many, -3, -2, -1, 0, 1, 3, this picture. So here we write the equivalence class for each element of the set Z. So here we write the equivalence class, start with the 0 to write the equivalence class of 0. That means this equivalence class contains those elements who related with the 0. So now observe which element related with the 0. So this is nothing but our x element. This is our x. Now to find, and our condition is the x minus y is even number. So first element is the 0. Because 0 minus 0, answer is the 0, and 0 is the even number. So 0 related with the 0. Now for 2, 0 minus 2, answer is the -2, -2 is the even number. So 2 is related with the 0. Similarly 4, 6, 8, etc. And negative sign, -2, -4, -6, -8. Okay. So this is the equivalence class generated by element 0. And observe this, all elements are related with the 0 because our condition is x minus y is even number. So all these elements satisfy our condition and all elements of this set related with element 0. So this called equivalence class generated by 0. Now to write equivalence class generated by element 1. Now you can write equivalence class generated by any one element. Any element of this set. Now here we write the equivalence class generated by element 1. So this set contains those elements who related with the 1. So our x is the fixed. Our x is 1. Our x is fixed. Now to find y. Now we find element y, which is related with the element 1. So here our element related with the 1 is, so here we write as the minus 1. Minus 1 related with the 1 because 1 minus 1 answer is the plus 2 and plus 2 is an even number. So minus 1 related with the 1. Minus 3. 1 minus plus 3. So answer is the 4 and 4 related with 4 is the even number. So minus 1 minus 3 minus 5 minus 7 etc. Similarly in positive side 1 minus 1 answer 0 and 0 is even number. Also related 3 5 7 etc. So now observe here all these elements related with the 1 because 1 minus all these elements answer is the even number. So all these elements related with the 1. So this is called equivalence class generated by 1. Now this is the equivalence class generated by 0 and this one is the equivalence class generated by 1. Now to write the equivalence class generated by 3. Suppose to write the equivalence class generated by 3. So this with the relation 5. So this set contains those elements who related with the 3. So this cell element contains the set minus 1 because 3 minus 1 answer is the plus 4 because 3 minus 1 answer is 4 and 4 is the even number. So minus 1 related with the 3. Similarly minus 3 minus 5 minus 7 minus 9. So all these elements related with the 3. Now in positive side 1 3 minus 1 2 related with the 3 minus 1 answer is the 2 and even number. So 1 is related to 3. Similarly 1 3 5 7 9 etc. So this is the equivalence class generated by element 3. Now observe equivalence class of 3 and equivalence class of 1 both are the same. Equivalence class generated by 3 and equivalence class generated by r is 1 is equal to 3. The equivalence class of 3. So after some equivalence class, your equivalence class are repeated. So here to find the equivalence class of 2, so equivalence class 2 is nothing but the equivalence class of 0. So equivalence class of 0 and equivalence class of 1 are same. So here we find the equivalence class for each element of the set Z and observe this equivalence class. After some equivalence class, your equivalence class becomes equal. So here we find equivalence class of 0 and equivalence class of 1. After that we find equivalence class of 3, 4, 5 are repeated, either equal to 0 or either equal to 1. So here we find two equivalence class 0 and 1. And now observe here, if we doing the union of equivalence class 0 and equivalence class 1, then answer is union of equivalence class 0 because equivalence class of 0 is one kind of set and equivalence class of 1 is also set. So if we doing the union of these two sets, if these two sets, then our set contains the element 0 minus 1 minus 2 minus 3 minus 4 minus 5 minus 6 minus 8. In positive side 1 2 3 4 5 6 7 8. So this is nothing but the what Z. So if we doing the union of equivalence class 0 and equivalence class of 1, we get our set of integer Z. So this is the topic of the equivalence class. Now we will first define the definition of equivalence class. R equivalence class. Let R be equivalence relation. Equivalence relation on set A. Now for any, now we can write the equivalence class of any element of set A. So now for any x belongs to A, now for any x belongs to A, this set Y where x related to Y. So this set contains those elements who related with the x. So whenever you write the equivalence class of x, so equivalence class contains those elements who related with the element x. This set is called equivalence class, R equivalence class. Generated by element x. So this is the equivalence class of x, and this is the equivalence class generated by element x. It is denoted by notation close bracket x, and this is this. And so finally we write as the equivalence class x this is the equivalence class of x generated by element x. And now observe here equivalence class x is always subset or equal to our set A. As seen in our next example, when we bring the union of equivalence class 0 and equivalence class 1, we get the answer Z, and Z is a subset itself. Then observe equivalence class 0, here we obtain equivalence class 0, -4 -2 0 2 4 is, so equivalence class 0 is subset of Z. Our equivalence class 0, -4 -2 0 2 4 is a subset of set of integer Z, and equivalence class of 1 is also subset of Z. So whenever you find equivalence class generated by any element of set is always subset of your set A. Whatever set we have given, in this example we have given the set Z. So each equivalence class of Z is subset of set of integer Z. With that as our result, equivalence class is a subset of set A. Now we see examples. We already discussed. Consider first example. A is equal to 1 2 3. So here we find the equivalence class generated by 1 2 and 3. So first of all we define our definition say our relation be equivalence relation. Equivalence class find those sets if your relation is equivalence relation. So our relation is defined as So relation R is equivalent relation. Now to find equivalence class 1, 2 and 3. So first we will find equivalence class of 1. So observe here, which element related with the 1 in relation R. So here our is the definition containing while where 1 related with the 1. So here 1 related to 1, we write as the 1 related to 1. Here write as the 1 related to 2. So our x element is 6 to find the y. So our y is 1 and 2. So equivalence class of 1, 2. And observe, equivalence class of 1 is subset of A. Equivalence class of A is subset of set A. Now you can find equivalence class of 2 and 3. So here we find the equivalence class of 3. So which element related with the 3 in relation R? Just one take 3, and 3 related with itself. So answer is just 3 and subset of 2. So this is the equivalence class of relation R 1 and 3. Now we take another example. Let Z be set of integers and we define relation R as xy where x minus y is even number, and we already proved in our previous lecture our relation R is equivalent relation. So here not need to check our relation is equivalent or not. So relation R is equivalent relation. Now to write the equivalence class of any element of the set Z, and Z contains infinitely many elements. So here we write the equivalence class of 0 first of all. So equivalence class of 0, which element related with the 0? So those elements related with the 0 will satisfy this condition, x minus y is even number. So our x is the fixed 0. Now to find y, and answer becomes the even number. So minus 4, minus 2, 0, 2, 4, 6, etc. So all are these elements related with the 0. So now this is the equivalence class generated by 0. Now we write the equivalence class generated by 1. So we already know which element comes in equivalence class generated by 1. So contain the elements minus 7, minus 5, minus 3, minus 1, 1, 3, 5. So this is the equivalence class generated by 1. Now we find the equivalence class generated by 2, 3, 4. So value of equivalence class 2, 3, 4, 5 either equal to 0 or either equal to 1. So these are disjoint equivalence class. And observe here, equivalence class 0 and equivalence class 1 subset of our set Z. As our note, any equivalence class is subset of set A. Now if we doing the union of these two sets, we get our set Z. So this is the example of R equivalence class. Now we next discuss about the quotient of A by R. Now if we doing the union of, now if we write the one another set of all equivalence class, if we write the set as now this is the set of equivalence class. This is the set of equivalence class. So this set is called quotient of A by R. This set is called quotient of A by R. So in short, quotient is nothing but the collection of collection of all equivalent class is called quotient of A by R. Here our A is Z, so here we write our set Z. So here we find the equivalence class 0 and 1, and equivalence class 2, equivalence class 3, either 0 or 10 is 0 or 1. So here not need to write. So if we make the set with equivalence class 0 and 1. So this set is called the quotient of Z by R. It is denoted by notation Z by R. This is the notation to denote quotient of Z by R. So quotient of Z by R is nothing but the set of all equivalent class. Now to write the quotient of, in this example, our equivalence class is 1, 2, 1 and 3. Here we find the equivalence class of 2. So equivalence class of 2 in this example is the 1, 2. Now to write quotient of A by R, here we denote our set as A. So we write as the A by R. This notation read as the quotient of A by R. Here R is our relation, whatever relation we will define. Is nothing but so quotient of A by R is nothing but the collection of all equivalent class. So in our first example, we have 3 equivalent class 1, 2 and 3. 1, 2 and 3. So we are doing the set. So this called the quotient of A by R. So quotient of A by R is nothing but the collection of all equivalent classes. It's called the quotient of A by R. So now here we write the definition of quotient of A by R. Quotient of A by R. Let R be equivalence relation on say A. Now quotient of A by R. So the collection of all equivalent classes of set A is called quotient of A by R. Is denoted by notation. So quotient of A by R is nothing but this. So quotient of A by R is nothing but the collection of all equivalent class. Every A belongs to A. It's called the quotient of A by R, and this noted by this notation, and this is the quotient of A by R. So this is the definition of quotient of A by R. And we see in next example to write the quotient of A by R is, we already see how to write the quotient of A by R in our previous examples. So now today we stop here. In next lecture we will discuss properties of the R equivalence class. So there are 4 properties of the equivalence class. So property of equivalence class we will discuss in next lecture. Thank you, good luck, and thanks for watching this video.